So we have stated the coarea formula. Now we will show you some application of this result. Example. We take this function f. Fx is precisely the norm of x. Then we see that we will compute the gradient of f, because in the coarea formula we have the gradient, the norm of the gradient. Therefore, we need to compute the gradient. Computing the gradient is computing the partial derivative of this function. So this is the norm of x is precisely the square root of j from 1 x j square. So this is by an easy computation, square root is 1 over 2, and the derivative of this sum, j from 1 to 3 xj square. Okay, so this is xj square, the sum of xj square, taking derivative which is with respect to xi. Only the term j equal to I survives. Other terms are 0. So we only have 2xi, and the square root in the denominator, and then this is xi. Then the denominator is precisely the norm of x. So we have compute the partial derivative of this function. So the gradient of fx is precisely x1 xn. Maybe I don't write it this way. So x1 norm of x, xn norm of x. So this is precisely x over the norm of x. So we see that the gradient is 1 for any x, not 0, because to computing the partial derivative in this step, we need x not 0. If x is 0, this step is not true. Okay, but for point other than 0, this is okay. Now, we also have a result in our quiz. In our quiz, we know that for a function g, the integral of g over a surface which over a sphere which radius t, maybe I will use g, equal t square, the integral over sorry, this is d sigma, surface integral. We have this result in our quiz. This is why I put this question in the quiz. Okay, using this result, we can compute the following integral. The unit sphere, the norm of x. This is by coarea formula. That is gx. In coarea formula, we take gx to be the norm of to the power 4, and the fx to be the norm of x. So using the coarea formula, this can be written as 0 to 1 dt. Then f equal to t. Gx, that is x to the square, and the gradient of f d sigma. But the gradient of the norm of the gradient is 0. So this is 0 to 1 dt. F equal t x4 d sigma. But fx is the norm of x. X equal to okay, we use the we have two methods to compute this. We can either use the result in the quiz here. Using this result, you integral over a sphere of radius t, can be transformed into an integral over the unit sphere, but which a t square here, and also a t in the variable. Okay, so using this result, our computation can be continued to be 0, 1, t square, f equal to 1, then ty4 d sigma, then dt. Just using this formula, g is the norm of to the power 4. So, okay, this is the first method to compute this. So this will give us 0, 1. So consider this integral. This is the t to the power 4. Because y lies in the unit sphere, because f equal to 1 is the unit sphere. So this is bt, boundary of dt, and this is the boundary of b1. So y in the boundary of b1, the unit sphere, the norm of y is 1. Therefore, this is just the t to the 4. So altogether we have t to the 6. T to the 6. And then the integral of the unit sphere, d sigma, then dt. So the integral over the unit sphere is precisely the area of the unit sphere. We know that this is 4 pi. So this is 4 pi 0 to 1 t to the 6 dt. So the final result is 4 pi over 7. Okay. So using coarea formula, we can easily compute this integral. Of course, in this computation, it is important to use the result in our quiz. That is the last line in this page. We can transform an integral over a sphere which radius t to an integral over the unit sphere. Okay, so this will make our computation easy. Of course, for our particular gx here, in this example, the gx is quite special. It is a very simple function. So in this step, we can also compute the result directly. So in this step, we can also go this way. That is 0. Maybe I will change a color. 0 to 1 dt f equal to t. Then this is just t to the power 4 d sigma. Okay, because on the sphere, on the surface f equal to t, that is the sphere which radius t, the norm of x is just t. When x lies in this sphere which radius t, the norm of x is t. So this integral, the integral here, become the integral I write here. Okay. Okay. So now for this integral, t is a constant. Okay. So this is equal t4. Then the integral of f equal to t d sigma, then dt. But the integral of the constant function 1 over f equal to t, that is the sphere which radius t, is the area of the sphere which radius t, which is 4 pi t square. And as before, this is also 4 pi over 7. Okay, so this is the application of the coarea formula. Very powerful formula, very useful. And although it's very important and very useful, but unfortunately, we could not provide a proof of this theorem. And when I'm teaching this course in Xiamen, I use ordinary differential equation to prove this theorem. But due to the time limit, I cannot do this here. Next, we consider our another topic, the green and the Stokes formulas. Green formula. Firstly we need to consider some special two-dimensional domain. So let phi plus a minus define a minus a plus in this interval, real valued, continuous function. Then we can define that if this function satisfies the condition that phi minus always no greater than phi plus, that is, this is x-axis, this is y, so this is our interval a minus a plus. We have two functions, one is always less than or equal to the other, so we have two functions. So this is y equal to phi plus x, and this is y equal to phi minus x. So phi minus always no greater than phi plus. That is, the graph of phi minus lies below the graph, that is the curve of phi plus. Then we have a region here, omega. This region is what we call the simple region, simple domain. So our omega consists of all such xy, where x belongs to the a minus a plus, and the y belongs to the so this omega consists of all such points. For given x in the interval, a minus a plus, the y can be chosen between these. Given another x, you have another y. The other range of y is here. So this indicated that our omega is such a domain. And the boundary of this omega, consists of this curve, the graph of phi minus, and the graph of phi plus, and also possibly the vertical part of the boundary. In this picture, we have a vertical part, and the left, we have a vertical part on the right boundary. The left boundary might also has a vertical part, but in this picture, the left vertical part shrink to a common point, which y coordinate phi plus a minus equal phi minus a minus. That is, the two are coincide. If this is strictly greater than this, then they determine the vertical part on the left. Okay, that is the picture in that can be shown in the next picture. That is here, a minus a plus, and this is y equal phi plus, this is y equal phi minus. Then we have a vertical part on both sides. Then the orientation of the domain bounded by this curve and the possible vertical part is what we call the simple domain. And this is the domain that we mentioned when we proved the generalized Forbini theorem. Okay, so the boundary consists of 4 or 3 or even only 2 parts. In the picture below, the boundary consists of 2 curves and 2 segments. The orientation is chosen in this way. The lower boundary will go from left to right, and to the right boundary we go up, and then on the top boundary we go from right to left, and then on the left boundary we go down. Okay, this is the orientation to the boundary of this domain omega. Okay. So for such orientation is called positive. That is, when you go along the boundary, the domain always lies on your left. Positive oriented. Or any planar domain omega, we can always define the positive orientation on the boundary. Positive orientation. That is, you go along the boundary, the domain always lies on your left. For example, this is a somewhat complicated example. The domain is bounded by these three closed curves. Our domain is here. The domain is here. Okay. So the boundary consists of these three closed curve. So the orientation on the outer boundary is given this way. Because you go in this direction, the domain omega lies on your left. But the orientation on the other part of this domain, so this is this way. So that you go along this curve, the omega lies on your left. Similarly, this part also the orientation is oriented in this direction. Okay, that is, in the outer boundary curve, you go anti-clockwise, and in the boundary inside the domain, you go clockwise. Okay. So this is the orientation. Such orientation we call the positive oriented. Positive oriented. So we define what we say the positive oriented in this manner. That is, when you go along the boundary, the domain lies on your left. Okay.